membrane fouling and control. I'm Wei Wang from Harbin Institute of Technology, School of Environment, and I will be co-chairing today's panel. Today, we will have 4 presentations in total, and each presentation should control in 15 minutes. And the first speaker is Professor Lin Saisai from Zhejiang University. He will give us a presentation. I would like to share to give this floor to Professor Lin. You can share your screen right now.
Okay. Yeah. Oh, okay. Thank you, Professor Wang, and thank you, Professor Mira. And good morning, everyone. My name is Saisai Lin, the postdoctor in Zhejiang University, and my work is focused on the development on the antifouling reverse osmosis membrane. And my collaborated mentor is Professor Lin Chang in Zhejiang University, and sorry. Today, I would like to share our work that titled "Enhancing Antifouling Property of Reverse Osmosis Membrane, the surface tested with ionic liquids." And we'll introduce this work in following the 3 parts. First is the background. By fouling caused by non-specific protein adsorption and would lead to the incompatibility of biochemical and analytic devices. This is due to the serious extensive protein adsorption on cell, and will cause the geometry of the cell and finally stick to the issue. And also you can see the performance deterioration of the membrane-based process. So therefore, the development of antifouling materials is highly desirable. And Switzerland has been regarded as an excellent for antifouling materials, and even so, I think it can be titled as a non-fouling materials. The Switzerlands are the polymers with content and balanced charge units that was stable bind with the hydrated water molecules, and it has been recognized possessing the non-fouling properties that can reduce the protein adsorption on growth by 99%. And this outstanding non-fouling property has been confirmed from the electrical neutrality and the stable hydration from the ionic solvation. And currently, its application on the non-fouling area has been extensive and very chemical stability, but it also has some issues on the polymeric surface, because especially on the delicate polymeric surface, because the problem was stemmed from the grafting approach and the raw materials. Currently, the grafting approach used for the sterilized application included the ATRP, that was a tedious process, and the ICVD, that was solvent-free but prone to deteriorate the separation and performance relationship of the membrane. And for the raw materials for the Switzerland, it was very limited, especially for the directly available Switzerlands. So the antifouling materials of industry value are highly needed. And we can analyze the antifouling mechanisms for the Switzerland. It was stemmed from the balanced charge that was come from the electro neutrality, and the stable hydration that was stemmed from the ionic solvation. So we we was to look into the ionic liquids. Such kind of green materials also consisted of it was very special because it was completely consisted of the cation and the anion. So it was completely present as electron neutrality, and also it was very highly hydrophilic because of the strongly ionic solvation, and also it has been confirmed it was even in the bulk water, it was also existed as ion pulse in bulk water with the Coulomb interaction, and it has been confirmed by the two-dimension vibration spectroscopy. So this kind of the ionic liquids was poured into the range of the antifouling materials development. And so in this work, we are looking to find the very solvent and green grafting tool strategy to graft the ionic liquids materials onto the delicate PAO membrane surface. So the work was the highlight of this research, including the three parts that for the raw materials, we can choose a wide range of the cation and anion of the ionic liquids. So it has a high design flexibility. And for the grafting approach, it was we designed the surface amination or the micro addition. Both are very mild and can carried out under the ambient temperature and pressure. So it was a mild and solvent-free process. And for this layer, it was ionic liquid layer. So it was we can design the cation cathode or the anion cathode or the cation and anion cathode. So this work was carried out into three parts. First was the cation cathode, solid cation cathode, and the second is the solid anion cathode, and the third is the cation and anion cathode to the PA surface. So first part is cation solid cathode to the ionic surface. First, we synthesized the amino containing ionic liquids, and we use the amine group on the end of the cation, and then to graft it to the PAO membrane, use the surface imitation catalyzed by the EDC and NH system. And then firstly, before to evaluate the antifouling performance, we want to evaluate the ionic structure and its formed hydration layer on the PA surface. So first, we established we established 4 models on by the molecular dynamic simulation. First is the PA-PEG. That means we grafted the PEG onto the PA surface, and then the PA-PZ. We grafted the Schweitzer onto the surface, and the third is the PAIL bromine. That is we tested the cation, the solid cation onto the PA surface. First, we compared the dipole and angles distribution of the water molecules in these 4 models. We can see that especially for the PA, our brown membrane, that means solid cation cathode PA surface, the hydration formed, you can see the dipole angles of the water molecule was very very even and highly similar to the Schweitzer surface and like the bulk water. So it was, which it means the hydration layer formed on the PAIL surface was quite similar to the Schweitzer grafted PA surface. It has this uniform dipole distribution, and when you look into the we look into the PA-PEG model, so especially in this region, minus 40 to the 40 degree, you can see it was a lot of the molecular water was focused into this region, and which it means what it was largely oriented the dipole angular distribution. So it was quite different from the PAIL. And then we also do the IDF curves for this for the for the tested ionic liquids and the free ionic liquids in the bulk water, you can see we compared the distance between the nitrogen atom in the canine and the bromine atom on the anion. You can see the distance was quite similar, quite close. So in this way, we think that the anion and the canine still formed in the pairs, ion pairs onto the PAR membranes after the tensor operation. So after that, we compared the membrane. We did the membrane characterization. When on the optimum condition, we can see we use the two parameters, that is zeta potential and is water contact angle. You can see when under the optimal condition, the zeta potential was balanced to 0 in the optimized concentration and the grafting time, and also the water contact angle was also come to the lowest value, which we think is the whole surface of the ionic ionic liquids grafted surface was come to the electron neutrality. And when also do the FTIT, you can see that the whole polyamide matrix peaks was remade, and especially at the 1038, the typical peak for the imidazoline that was could be found. So we think the canine AV-IM was successfully tested on the PARO, and because of the mild and solvent-free process, the whole separation of the modified membrane surface was quite similar to the Princeton membrane that was acceptable and quite unchanged. Was unchanged. And then we come into the antifouling property evaluation. We do the static and the dynamic evaluation. When for the static protein adsorption, you can see on the when it under the optimum opposite condition, the antibody IgG adsorption came into the lowest value, and also to the dynamic evaluation, both for the HA, AA, and BSA for the single fullerent dynamic antifouling process, the separations of the flux of the modifying the membrane was stabilized to near 95%. So we think the canine modifying the membrane was exhibit the excellent antifouling performance. Then we also to check the antifouling behavior of the canine after the ion exchange. That means we fixed the canine AV-IM and exchanged the anion with pair. We paired the canine AV-IM with the diverse anions. You can see we paired it with the different anions of diverse molecular size. What we found is that the whole ionic modified membrane remained stable and also exhibited the excellent antifouling performance, and especially for the ionic liquids that containing larger anion exhibit better antifouling performance because we think that was attributed for the lower charge density for the larger ion pairs. And also we collected the information on the water molecular numbers. What we found is for the canine paired with the different anion, the membrane surface was contained as a similar water molecular distribution to the PA Sweeter-Rhine grafted membrane. So we think it's the whole ionic liquid after the ion exchange was very stable. Then we do the second job that we just solely grafted the anion of the ionic liquids onto the membrane by the micro addition reaction. That was also a very mild and can be carried out at the ambient condition. So in this way, we choose liquid ion liquids that for the anion, it contains the alkynyl on it. That was ready for the micro addition, and this is also kind of the LCST, that is the liquid critical solution temperature ionic liquids. When it was, that means it was lower the critical temperature, it will have this phase separation with the membrane. And when it was higher the critical time, it will have a strong bond with the water molecule. So also we check the membrane characterization. What we can see is theta potential also come to the 0 value when under the optimum condition. And after the grafting, the polyamide metric was remain intact, and also the anion C3S was found the typical sulfur acid peak in the FTIR, and also have the acceptable separation performance. Then we do the dynamic evaluation for these three membrane. We especially do the self-cleaning. We especially evaluated its self-cleaning ability. We do the 3 test cycles, which means that after the 8 hours following operation, we use the 50 DI water to wash the fold membrane, and you can see the water flux was recovered greatly compared to the Princeton and the BI grafted membrane. So it means when it was higher the critical temperature, the membrane will have the strong bond with water, and which will exhibit the excellent anti-fouling property. And third, we also do the cotasant surface modification. That means we tested the cation and the anion both onto the PA membrane surface. Also these micro addition. In this way, we choose the ionic liquids that both have the alkynyl on the cation and the anion, so we can to graft it both onto the membrane surface.
Please pay attention to the time.
Okay, so then it's also to the membrane characterization that was just like the same two. It was also the theta potential come to the 0, and also we have found the anion and the cation was successfully grafted to the membrane surface. And then we do the anti-fouling property. This way we do the properties. Foulant was at the high concentration. What we found, it was also exhibits the excellent anti-fouling property. So in this way, we just constructed a very green and solvent-free grafting modification to the delicate PAL membrane, and we use the ionic liquids to endorse the membrane with the excellent anti-fouling property. So by this way, we also this work was strongly supported by my professor Lin Chang and Zhikai Yao, and also the Dr. Ma Lie. So also we very thankful the national funding as below. So that's all. Thank you.
Thank you, Sese. Thank you.
Thank you.
Very good talk. I will open one question. You can post the question here. I see one question. Professor He asks, you fabricate the positively charged surface, right?
Yes.
In water solution, there are many kinds of negative charged organics. Will these organics fold the membrane surface? Please give a comment.
Oh, you mean that it will also cause the
negative charged organic polluted forward the membrane surface, the positive charged surface.
Okay. Sorry that maybe I did not speak very clearly. In the first part, we solely grafted the positive. That means we solely grafted the canine onto the membrane surface. But you can see, we have did the molecular simulation. Even we solely grafted the canine on the membrane surface, but the ionic liquids will still exist in the ion pairs. That means you can see like this way. The bromine was still distributed around the positive the canine. So the whole membrane surface was exhibit the electron neutrality. So we think that will have the higher anti-fouling property to the opposite ions.
Okay, many thanks. This question is from Professor He Tao. Let's thanks again. Now let's go for the next speaker.
Yes, thank you.
Okay, you can close your screen. Yes, the next speaker is from Zhejiang Normal University, Professor Yasin Arouzi. Let's welcome. You can share your screen.
Thank you, Weiwan. I'm sharing the screen.
Yes, you are sharing. You can.
I reshared the screen.
Yeah, I see.
Thank you, Weiwan, for your introduction. I will talk about luminointensity of biofoulant. And as introduced, I'm from Zhejiang Normal University. As a guest editor and reviewer, I'm serving more than 80 SCI journals. And I have 26 highly cited and 10 hot papers. These are the contents of my presentation, and I'm interested in designing, synthesizing, and developing of novel multifunctional nanocomposite materials with over hundreds of SCI papers. And this is my career background, some of my findings, and main nanomaterials that I'm using in my research works, my industrial experiences, and teaching experience, and some awards. Process intensification tightly integrated with environmental engineering, and I will talk about membrane role in process intensification. For sustainable growth and decreasing production costs, equipment size, energy consumption, waste production, and increasing efficiency, remote control, which is very hot topic during the pandemic, and information fluxes and process flexibility. Many concerns of today could be solved by membrane engineering, which is mainly divided to water purification, energy consumption, energy application, and environmental. Also, we have further applications which considered as minor. We have two phenomena for separation. One is filtration and another is diffusion. By taking a look over 50 years of industrial history of membrane plants, we would see after 50 years, we met a plateau, and this plateau has yesterday, Professor Warren said, met thermodynamically calculated plateau. But if we go to very advanced membrane plant, we would see the actual energy consumption is 3 to 4 kilowatt hours per cubic meter because of pumping, pre-treatment, post-treatment, and fouling. These 3P are at the edge of technology, but we can still do something about fouling, which is accumulation of foulants on the feed side of membrane. We have 4 types of fouling. Colloidal and scaling could be solved by feed pre-treatment, and organic and biofouling could be solved by membrane modification. Biofouling includes 5 stages, and when we enter the 4th stage, we would lose the membrane very quickly. So it is important for timely detection of interval between phase 3 and phase 4. In membrane technology, we take care of high performance and low cost. This is why we are usually using mixed matrix membranes. And it is very hot topic, at least in Elsevier. In recent 30 years, we can see the progress of attention for blending. These are my contribution to the membrane society. For the first work, we use anti-fouling filler to kill the bacteria, and it increased bactericidal effect from 2% for pristine membrane to almost 100%. These are the details. And another remedy is decreasing adhesion of foulants. By using mesoporous carbon, we decrease the adhesion of protein and bacteria. And you can see biofilm formation reduce over 90% of adhesion of protein and bacteria for the sample which doped with only 0.2% of mesoporous carbon. By mixing these 2 remedies, bactericidal and anti-adhesion, we can see the third work with very small amount of silver, we got even better results. This is for biofilm formation, and this is synergetic effect of silver and mesoporous carbon for both gram-negative and gram-positive bacteria. By comparing these 3 works, we came to real-time PCR for selecting best samples and selecting the comparable part of bacteria, which is highlighted here. And after 2 days, you can see the big difference between pristine membrane and modified membrane, especially this silver-doped mesoporous carbon. But it is hard to make new membranes and industrializing them. So we came to this idea. If we go through the another accessory for not competing with the current industry, but adding value to the system, we came to the topic of today, which is luminescent film, which is patented and is one of the highly cited papers for 3 times. The point is it can detect the interval between maturation first and second, as formerly said, because if we wash the membrane after entering maturation second, we would have irreversible flux decline. Many techniques formerly used in this regard, but most of them didn't industrialize. And the value is about 15% membrane cleaning, cost decrease, and capital expenditures for membrane replacement could be decreased up to 10%. Also less maintenance and effective chemical consumption for CIP. These are the results of TPE. And you can see the particle size here and TM results and pore size. We simply mixed matrix membrane casting with phase inversion, and after that you can see many of results were comparable for PS Lumi 5 and PS Virgin. Even for XPS, they had good similarity. For DSC, it was identical because of the nature of TPE. And here you can see flux increase is normal because of the agglomeration regarding to the TPE particle mixing. And even for bacterial effect, it was identical, and also for BSA adsorption plus bactericidal effect, which determined by phelocytometry. And you can see the trend by addition of the luminescent material, the intensity increased. But the point is, when we increasing the TPE up to 5%, it is not high intense for fluorescent emission when it is not foul, but after fouling, it's got 2,400 almost AU, and the difference is about 1,000, which is detectable. This is the optical photos in dark room and normal room, and this is the trend of increasing the intensity when we sum up the former slides figures. And you can see this sample was far better than other samples when we conclude the results. And nowadays we are working on making the setup for actual detection and pilot stage. This membrane also could be used for biomedical applications or mechanical applications. Many papers and patents are useless for contribution to the society. We recently published on Science, and these are my results from Microsoft Academic, which break the restriction on saliency of publication, and my citation map from all over the world, Western countries, United States, and even MIT. Also, we have citation from Nature, Science, and Cell Press. I have a few special issues. One of them would be finished at the end of this month on membranes, another on food and chemical toxicology. With these topics, and you are welcome to submit to environmental research as well, which would be finished at the beginning of next year, and also chemosphere. I'm also looking for 3 postdocs, mainly from Chinese because of the restriction for traveling, with 250,000 yearly salary, and 50,000 RMB per year as funding. And after doing good job, the candidates will be introduced to my worldwide collaborators, or they could become a faculty member in Zhejiang Normal University. Thanks to my international collaborators and my great supervisor, my team, and sponsors, and great support of Amir Razvu. Thank you.
Yasin, I think we go to quick Q&A session. I don't know why Professor Wei Wang is not here. I would like to apply your postdoc position because you will give us 2.5 million RMB per year. That's a really high salary, huh?
Maybe 1-0 difference.
Okay.
This is just for advertising to attract.
That's too much.
So for everybody, you can type the questions in the QA, and at the same time, you also can provide your name. We can ask the questions. I have one question for you. So
Yes,
because my research is about the nanofiltration, so I also have a very your research is very interesting. Can you just show me simply about your research, because I don't very understand about your luminol for your research. Can you just simply explain this? Yeah, because I'm very curious about this. Thank you.
As I formally said, there is 2 maturation stages. Formerly in the literature, they address as 1 stage. And for higher flux, long-term stability, and also application in industry, we need timely cleaning place. The idea was industrial, but if you want to use it in scientific aspect, when you are making nanomembranes, you just add some luminescent material which couldn't be detached from your membrane. In this case, if you are working on fouling, biofouling especially, you can get very good results. And by adding a sensor at the top of the membrane, we have another parallel module which could be simulate the actual fouling in the industrial module. You can get the alarm for cleaning place even automatically.
That's really interesting. Thank you for your good suggestion. Yeah, I think maybe in the future I can also use the developed the materials for the computation with the nanofiltration process. Yeah.
Sure. We have in this slide I address, we have a lot of materials, even we can produce in mass branch. If you interested, I'm happy you can contact me.
Yeah, of course. Yeah, I'm very interested with that. Maybe we can, after this meeting, we can have some simple talk to maybe have some interesting research. Yeah, thank you, Yasin.
My pleasure.
Okay, so now we will welcome the next speaker. Yasin, can you stop the sharing your screen?
Yeah.
Yeah, thank you.
Can I share my screen?
Yes.
Okay. Can you see my screen?
Yeah. Yes. Yes, we can see. Okay. So I will give you a simple introduction. So now is for the we welcome the Dr. Toru Miwa. He will give a presentation entitled Geofouling Development in MBR Treating Real Sewage Under Low Temperature Condition. Okay, welcome. So now you can continue.
Okay, thank you very much for your introduction. This is Toru Miwa from Department of Science of Technology Innovation in Nagaoka University of Technology from Japan. I'd like to start my presentation. The presentation title is Geofouling Development in MBL Treating Real Sewage under Low Temperature Condition. The significance of this research is the one is the MBL operation condition which caused geofouling was first discovered. And also that this research indicated that geofouling cause might be due to the influent deposition on membrane surface. Firstly, I'd like to introduce membrane bioreactor. A membrane bioreactor is a system which is combined membrane separation technology and biological treatment process. MBL has been installed in many wastewater treatment fields because MBL has advantage to conventional activated sludge system, such as high quality effluent and compact occupation area, high MLSS concentration. However, with continuous operation, biofilm is formed on the membrane surface and covered membrane pores. As a result, membrane flux significantly decreased. This phenomenon is called membrane fouling and lead to operational cost increase by membrane replacement and membrane wash. Further MBL installation, membrane fouling still has been needed to be solved. Membrane fouling can be classified into two types. One is cake fouling, the other is gel fouling. Cake fouling was developed by cake layer biofilm. The appearance is shown in left figure. Black granule matter were scattered on membrane surface. The feature is slow TMP increase about 1 month and low effective permeability. On the other hand, gel fouling was developed by transparent gelling layer biofilm, as shown in right figure. The feature is fast TMP increase 1 to 2 days and sudden development and fire effects to permeability. Therefore, gel fouling must be solved to achieve stable operation of MBL, treating real sewage. But problem is operating conditions of gel fouling is unclear. And also the gel fouling cause could not be investigated. So the gel fouling research has been conducted using model gels. In our group, we discovered operating conditions which cause gel fouling in MBL treating real sewage. Therefore, using this method, we elucidate gel fouling cause by investigating into physical conditions of activated sludge and membrane fouling caused matter and microbial community of activated sludge and biofilm. So for the research, we used two of non-oxyc membrane bioreactors. The one, named S1, was operated as control. The other one, named S2, was operated as gel fouling causing reactor. Both reactors were installed in sewage treatment plant in Nagaoka City, Japan. And the sewage secondary effluent from the plant was used for influent for MBL. Anoxic tank and oxyc tank volume was 5.5 liter respectively. We found that organic loading rate change condition was a factor to induce gel fouling. Activated sludge temperature was controlled by water jackets and installed on the side of tanks. The operation period was divided into the 4 periods to induce gel fouling. Stable operation, period 1 and 2 and 3. The OLR was increased period by period, as shown in this table. This is more detailed operational conditions. We use the real sewage as influent, so we cannot control the organic concentration in the influent. Thus, to achieve OLR change in the S2 reactor, a certain amount of active sludge was discharged from oxygen tank in the beginning of each period. Therefore, the MLSS was decreased from stable operation to period 1, 2, and 3. To maintain the MLSS in each period, SLT was also changed. HLT is 5.5 hours in both reactors, and the reactor temperature was maintained around 11 Celsius degree. And the analytical item were shown in this slide. For membrane fouling monitoring, the TMP and flux were measured. And also for checking the active sludge filtrability, filtration quantity of active sludge was measured using 1.0 micrometer filter. And also membrane fouling causing matter such as protein, polysaccharides, and TOC, insoluble microproducts, named as SMP, were measured. And also using the 16 sRNA gene sequence analysis, microbial community of active sludge and biofilm are also analyzed. So this is the result. At first, I'd like to show you the permeability of S1 and S2 reactor. In S1 reactor, membrane permeability was almost stable, and membrane fouling occurred 5 times through full operation. And cake layer was formed on the membrane, as shown in this figure. On the other hand, permeability of S2 reactor was fluctuated, especially in period 2 and 3. Membrane fouling occurred 1 times, 4 times, 9 times in period 1, 2, and 3, respectively. As shown in this picture, in period 3, gel layer was formed on the membrane surface. Membrane gel fouling frequently occurred in S2 in period 2 and 3, and gel biofilm was formed on the membrane surface. This slide shows the filtration quantity of AS in the oxygen tank. Normally, the activated sludge filtrability has a significant effect on membrane fouling. Filtration quantity of control S1 was 5.6 milliliter per 5 minutes. But the filtration quantity was in S2, filtration quantity of S2 was increased period by periods. It is indicated that AS filtrability was improved period by period, whereas membrane fouling occurred most frequently in period 3 in S2. It is indicated that active sludge filtrability was not related to the gel fouling. SMP of protein and polysaccharides were also measured. When these protein and polysaccharides concentration was high, it is known that membrane fouling occurred easily. But polysaccharides and protein concentration was decreased period by period in S2 reactor. It is indicated that the AS active sludge was changed to be less prone to membrane fouling. This graph shows the TOC concentration in the SMP and the influent TOC concentration. TOC concentration of S supernatant in S2 was also decreased. TOC concentration of AS was higher than influent concentration in S1 and stable operation in period 1 in S2. This might be due to the accumulation by sludge autolysis. And also in period 2 and 3, the period which membrane fouling occurred frequent, influent TOC was higher than SMP in active sludge. It is indicated that the difference of TOC was degraded or attached onto the membrane. And also the TOC concentration in SMP per 1 gram ml VSS is shown in the right figure. The TOC concentration per ml VSS showed almost similar through the whole operation in S1 and S2. Therefore, the production and accumulation ability per ml VSS was similar. It is indicated that the infant TOC might not be degraded well in activated sludge. So this slide shows the microbial community of activated sludge and biofilm. In period 2 and 3, which is scale fouling was observed or investigated, microbial community of activated sludge was almost stable in both reactors through whole operations. On the other hand, microbial community of biofilm was significant difference between S1 and S2. In S2 biofilm, Campylobacteriaceae, which frequently observed in real sewage, was the most dominant bacteria in period 2 and 3, whereas not in the S1 in period 2 and 3. In addition, uncultured bacteria, OD1, was also observed in period 2 and 3. It is indicated that the Gale biofilm is a unique environment for microorganisms, and also this result suggested that the infant composition might be attached onto the membrane surface in period 2 and 3 in S2. So this is a summary of research. The purpose, we investigated the cause of gale fouling using actual sewage, which was previously impossible. The result is permeability was declined in S2 gale fouling reactor, and gale biofilm was formed on the membrane surface. Activated sludge filtrability was increased, whereas membrane fouling causing matters were decreased. Activated sludge properties did not have effect on gale fouling. And also the Campylobacteriaceae and OD1 was dominant in the biofilm in the S2 reactor. Campylobacteriaceae were frequently observed in real sewage, so gale fouling might be caused by development of gale biofilm composed by influence substances. Thank you for the kind of listening. The funding is shown in this slide. Thank you very much.
Thank you very much, Dr. Toru. Very nice presentation. So, are there any questions?
Is it possible to ask question in the room, or we
Yeah,
must
if you,
like,
you can, if you are interested in, you can directly ask him. It's okay.
thank you, Toru. Would you please go back to the methods?
Okay, please wait a moment. Which slides?
Thank you. Yeah, I missed this slide. Would you please re-explain the method? Thank you.
Okay, so whole methods that you mean?
As far as possible, because maybe we have 3 minutes.
Okay, the methods is we use the two of anoxic membrane bioreactor. Other one is for the control, named as S1, and then the S2 is a gale fouling cause reactor. So we, under gale fouling in the S2, we operated this reactor for the gale fouling condition. The condition is organic loading rate change. So we separated the operation times into the 4 periods. The one is a stable, and second is a period 1 and 2 and 3. And then in each period, the OLR is getting increased period by period. And then this is a detailed fouling condition, HLT, SLT, MS, and temperature. The temperature is 11 Celsius degree, so it is a condition in a MBR condition in the winter, and the MLSS is was around this, and then we we use the real sewage influence, so we cannot control the OLR by changing the organic concentration in the influent. So we discharge the sludge in the beginning of each period. And the SRT was also changed for the maintaining this MLSSS. Also, these are the shown. This slide show the analytical items. Can you understand a little bit?
Yeah. And I have curiosity how this method lead to the bar chart in the results.
Sorry, I cannot hear. Can you say it again?
There was a bar chart in your results before the conclusion. How
Bar-
this method?
bar chart.
This,
One.
yeah.
Okay. So this one, from the left, this one, the S1 reactors microbial community. The two of these are the activated sludge microbial community, and these are the next two is biofilm, and each one is the period 2 and period 3 of activated sludge, and the period 2, period 3, and biofilm. And in the right here is S2, AS activated sludge, period 2 and period 3, and period biofilm for the period 2 and 3, period 3. The geofouling was caused, observed in the S2, and then I scrapped the biofilm from the get biofilm. S2 in the S2 reactor, and then I analyzed the microbial community, and I found that Campylobacter and OD1 were predominant in gel biofilm. Then Campylobacter was frequently observed in the sewage and the influent, so influent composition might be attached onto the membrane. Then gel biofilm is formed. It is indicated.
Thank you very much. Very nice work.
Thank you for the question.